Hi everyone. Today let's look at the problem 236, LeetCode problem 236, lowest common ancestor of a binary tree. Given a binary tree, so let's be very clear, it's a binary tree, not a binary search tree. Okay. Find the lowest common ancestor of two given nodes in the tree. So we have to find the common ancestor which is for two given nodes. The lowest common ancestor is defined between two nodes P and Q as the lowest node in tree that has both P and Q as descendants. So what this refers to is, so assume that we are looking for 5 and 0. Then if you see 3 is the lowest common ancestor for 5 and 0, because if you see, this is the node in which both 5 and 0 are diverging or are in different subtrees. Okay. Now, one important thing is, as you can see here, both P and Q will exist in the tree. So this is a very important precondition for this problem. So without that, we will not be able to arrive at this particular solution. So now let's try to understand the induction here. So now let's take a case where we want to look into P6, which is this node, search for this one, and Q is 4. Okay. Now what we will do is we will start searching, we will do a kind of an LRN kind of searching. So basically we will do pre-order traversing. Okay, a kind of pre-order traversing. So let's do this way. So now we'll start with the left node from 3. So we'll come here. Okay, we didn't find a match, so we'll go to its left. Okay, now here we see a match. So at this point, what we'll do is we will return address of 6. Okay, all right. Now what will happen is, from here we will also traverse the right side, right? So it will come here. From here it will go to the left node. 7 will go to its left child, for which it will return null. Okay, same way it will get this as its null. Then it will try to traverse its right node, for which it again gives back null. Okay, because you didn't find the node. Now, so of course 2 will get a null on this side, but it will get now then it will go to its right side. Okay, so far so good, right? Now 4 is found. So when you find the node, you just return the address of that node. Okay, so as we come this path, now if you see here, okay, now this is the tricky part. Okay, now when you come to 2, since only one of the nodes, so we go for its left part, it got null, and for its right subtree it got not null. Okay, so then that means so this is basically we only found 4, so we'll just return 4 here. Okay, so for whichever part we got not null, we will just return that one. So now at 5, since we got both 6 and 4, its left and right are not null, then that means this is a diverging node, or this is a common ancestor. So what will happen is, if this is the case, then we will return 5. Okay, but at 3 it still doesn't know whether we already found all the nodes. So what will happen is, from the root it again goes to the right. Okay, it goes through this path. This will give it null, because since it couldn't find the node. Same way, this also will return null, and this also will return null. So now what happens is 3 will return. At this point we will just return 5, because only one of the nodes is not null. So this is the induction behind the problem. And so in simple terms, basically what we will try to do is, we will start traversing left, right, and then go to the node. So what will happen is, if as soon as you find the node, you will return the address of that node, and at the parent node, when you get both your left and subtrees, right subtrees, if either one, only one of them is not null, then you will just pass that whatever is not null up. Okay. If both are not null, then that means this is the divergent node. So you will actually pass the address of that parent node up, because that is the common ancestor. Okay. It will become much clearer with let's take another example. Okay. Now let's see that we want to find 6 and 0. Now let's apply the same case, right? First we'll start going left. Of course we found 6, so this will be 6. Okay. And it will go this route, this will return null, so this is null. Same way this also will return null, because it couldn't find the node. So on this side this will be null. Okay, so now at 5 we have only this left node, so we will just tell that we just found 6. Okay. Now at 3, now it will go to its right side, it will come here, it will find 0 here. Okay, here you will return the address of 0, here it will come here, it will return null. So since this is the one, only one is not null, we will just return 0. So this means that 3 is the first node with both 6 and both its left and right as not null. So this means we will return 3 as our final output. Okay, now I believe this is clear. Now let's take a case where P is an ancestor of Q, or Q is an ancestor of P. So basically the idea is that we need to find this way. Okay, so one of the nodes is already an ancestor of the other node. So how this works, let's see. So as soon as we come here, this node is found. So this is very important. This approach assumes that both nodes are always present in the tree. Okay, so as soon as it comes here, it will return the address of 5. Okay, now it will go through the left path as before, and this will of course return null. Same here, it will go here, this also returns null, this gives you null, so here we will give back 5. Okay, now okay, so for this one, of course the time complexity will be order of n, and space complexity will be the height of the tree. So you can put it as order of n. Okay, now let's code this up. So what we do is, if root equal to null ptr, all right, or I can make this condition split up, and then I'll put it together. So return root. So basically we came to one of the leaf nodes where we couldn't find the tree. Okay, then the other case is, if root, here we can use the address directly, or root equal to q, and that means we found the particular node, we will just return root. Okay, now the next case is, so we this is not a node where we found it, so we will just do a star L search equal to root of left p comma q. Okay, and we will also do a R search. Okay, if L search not equal to null ptr and R search not equal to null ptr, then this is the diverging node. Okay, so then what will happen is, when I mean diverging node, this is the node in which your P and Q are different subtrees. The first node where it is in different subtrees. So basically this will be the common ancestor. Then we can just return root. Okay. Now if L search, so then that means found only one data point. Okay, return L search if if R search, return R search. Otherwise, return null PTR. Didn't find L or R, sorry, P or Q in this path. We could simplify this further. So just to give you a heads up, this means we reach the root leaf node. Here, this is a case where either of the element is either equal to P or equal to Q. Then we can just return the corresponding node. We will so assume that is not the case. Then it's just an iteration path. So if this is the case, then we will check on the left hand side and the right hand side of the node. If both L search and R search gives you a non-null value, then this is the current diverging node. That means this is the lowest common ancestor. If not, we will first check either did we at least find one of them in the left search. If that is the case, we'll return the left search. If not, we'll return the R search. That's it. We could simplify this. Let's just run it. Then I can also simplify this a little bit further as a part of optimization. Okay, this looks good. If you want, what we can do is we can just make it this way, just to be a little bit more. Because at the end of the day, this is what it is doing. Okay, and this can be, as I can just return our search. Okay, so that's it for today. Thank you. Have a good one.